Okay, so we've talked about the operation of the MOS transistor in weak inversion, where current flow is predominantly by diffusion. And we've talked about operation of the MOS transistor in strong inversion, where the current flow is predominantly by drift. We'd like to get a handle on the operation of the device in moderate inversion, where the current flow is about 50-50 by drift and diffusion. Now, unfortunately, because both of these terms are equally important in this transition region, we can't neglect one over the other, and because of that, it turns out that it's nearly impossible to get a simple model that covers this transition region based on physics, just because the approximations that we make for strong inversion and weak inversion don't apply, and it's really hard to figure out how to make progress in this moderate inversion region. But it turns out that this moderate inversion region is going to be increasingly the most interesting place to operate the transistors for various reasons that it would be pretty difficult to get into in a very brief way right now. And so we're going to try to get a handle on this region of operation by taking a look at our strong inversion or weak inversion models and comparing them. So if you recall, our strong inversion model said that the current I was equal to the strength ratio times mu Cox over 2 kappa times max squared of kappa Vg minus Vt0 minus Vs and 0 minus max squared of kappa Vg minus Vt0 minus Vd comma 0. And the weak inversion model was I was equal to S, the strength ratio, times I0 e to the kappa Vg over Ut times e to the minus Vs over Ut minus e to the minus Vd over Ut. Now, even just comparing these two forms, we start to see some similarities. For instance, they're both proportional to the strength ratio S, and we've got this kind of prefactor here, and then we've got that multiplied by the difference of two functions that are identical, except one has Vs in it and one has Vd in it. And they both even have a minus sign. We can even take this e to the kappa Vg over Ut term and distribute it through the parentheses and write this as S times I0, and then write this as e to the kappa Vg minus Vs over Ut minus e to the kappa Vg minus Vd over Ut. And it gets even more similar because we have a kappa Vg minus Vs up here and a kappa Vg minus Vs down here, and we have a kappa Vg minus Vd up here and a kappa Vg minus Vd down here. So you may be thinking, well, this has a threshold voltage in it, a minus kappa Vt0, and this doesn't. But we can actually pretty easily put that in. We can always add 0 in the form of, in whatever form is convenient. So in this case, we could add 0 in the form of kappa Vt0 minus kappa Vt0. And doing that, we would get something like S times I0 e to the kappa Vg minus kappa Vt0 plus kappa Vt0 minus Vs over Ut. And then up here we have an e to the kappa Vg minus kappa Vt0 plus kappa Vt0 minus Vd over ut. And we can take this e to the plus kappa vt0 over ut that's common to both of these terms and break off that single exponential factor and factor it out. And rewrite this as s times I0 e to the kappa vt0 over ut. And what we're left with would be e to the kappa vg minus vt0 minus vs over ut minus e to the kappa vg minus vt0 minus vd over ut. And so now the resemblance is very close. We have the same functional form. The first term has a e to the kappa, or has a kappa vg minus vt0 minus vs, and the term down here has a kappa vg minus vt0 minus vs, and the same thing with the drain term, except the vs is vd. So that looks promising. And if we like, we can even put a 1 over ut in here by multiplying top and bottom here, by multiplying by unity in the form of ut squared over ut squared. We'll keep the ut squared upstairs in the prefactor, and we can take the 1 over ut squared, distribute it through, and then put it inside the max as follows. So we can rewrite this strong inversion current as S times mu Cox ut squared over 2 kappa times max squared of, now it's kappa Vg minus Vt0 minus Vs over ut, comma 0, minus max squared kappa Vg minus Vt0 minus Vd over ut, comma 0. And so now we even have the 1 over ut here that we have here. So it's the difference between two identical functional forms, and aside from the 0 thing up here, the argument of this max function is exactly the same as the argument of the exponential down here, and the argument of the second term is exactly equal to the argument of this term down here. And so that kind of suggests that we have some convergence, some very strong convergences between these two forms. And so, is it possible that we could find a function that would kind of approach this when, let's say, this is positive, and would approach 0 asymptotically when this is negative, in a way that makes something like an exponential approach to 0? Well, have we met a function like that? It turns out we actually have met a very closely related function. So back in PostLab 2, you were introduced to the soft the soft min function. Turns out there's a soft max function, which is very much like that. So soft max of, let's say, x and y, we could write as something like log of e. Let's say it's to make it somewhat adjustable. Let's say it's 1 over a times the log of e to the ax plus e to the ay. Well, if x is greater than y, that implies that e to the ax is much bigger than e to the ay, which implies that e to the ax plus e to the ay is going to be approximately equal to e to the ax. Well, that means that the log of e to the ax plus e to the ay times 1 over a is going to be approximately 1 over a times the log of e to the ax, which is just equal to x. So log undoes the exponential, the ax pops out, and we have 1 over a canceling with a. If x is less than y, that implies e to the ax is much less than e to the ay, which implies e to the ax plus e to the ay is just about e to the ay, which implies that 1 over a times the log of e to the ax plus e to the ay is equal to y. Okay. So, why don't we try putting in the softmax function into the strong inversion model and see what happens. Instead of carrying both the first term and the second term along, let's just concentrate on this first term, and that would correspond to the saturation current. So I'm going to leave the strong inversion and weak inversion models up here and basically concentrate on the first term. So we can write the saturation current I set on this hypothesis as S times mu Cox ut squared divided by 2 kappa times, well, it's going to be 1 over a times the log of e to the a times whatever this thing is, x. So it's going to be kappa Vg minus Vt0 minus Vs over Ut plus e to the a times 0 over Ut. And we're going to square that because it's max squared. So this is the softmax function replacing the max here. And we notice one thing right away, and that is that this is e to the 0 here, which is a 1. So this is equal to, so here we have a 1 over a squared, which we can pull out front into this prefactor. So it's S times mu Cox ut squared over 2 a squared kappa times log squared, like sine squared, and I'm going to put the 1 first, 1 plus e to the a times kappa Vg minus Vt0 minus Vs over Ut. And what we would like to do is to try to see what happens if this is our model in what would be the weak inversion region. And so that would correspond to when the argument of this exponential is less than 0. So what happens in weak inversion, i.e. when a times kappa Vg minus Vt0 minus Vs over Ut is less than 0. Well, if that's less than 0, then this second term here is going to be a very small number. Okay, very rapidly it's going to become a number that is much less than 1. So you might think, well, the log of 1 is 0, so it goes to 0. Well, it does, but we can actually do one better than that. When you took calculus, you may have been exposed to the Maclaurin series for log of 1 plus x as basically something like x minus ... I forget exactly what the series is. It's like x minus x squared plus x cubed or something like that. I think it's an alternating series, but it's basically approximately equal to x for x much less than 1. And so the log of 1 plus small is going to be just the small thing. So in this case, I sat would be approximately s times mu cox ut squared over 2a squared kappa times, well, we would get the log of 1 plus the small thing being approximately equal to the small thing, so we'd have the e to the a times kappa Vg minus Vt0 minus Vs over Ut, all squared, because it's the log squared. And so e to the 2a, this stuff, is what we would get. So we could drop the parentheses here and put the 2a here. And actually, that is going to be identical to this e to the kappa Vg minus Vt0 minus Vs over Ut, assuming 2a is equal to 1. So this is equal to e, well, it's equal to, what should I say, if 2a equals 1, which implies that a equals 1/2, then the weak inversion model matches. So making a 1/2 means that we would have, I guess I'll go back up here. Actually, why don't I just close all of this? So if a equals 1/2, we have that the saturation current would be equal to S times, well, the a squared was downstairs, so we had was mu Cox ut squared over 2 times a half squared times kappa times log squared 1 plus e to the kappa Vg minus Vt0 minus Vs over 2 ut. So the a upstairs here becomes a 1/2, and that makes a 2 ut downstairs. And so this 2 will cancel with one of these halves here, and that'll make the 2 pop upstairs. And so this is equal to s times 2 mu Cox ut squared over kappa times the log squared of 1 plus e to the kappa Vg minus Vt0 minus Vs over 2 ut. And so this thing has units of current, and in this model it is called the specific current Is. And by form-fitting here, Is is also equal to I0 e to the kappa Vt0 over ut. To make the weak inversion model match up, these two things have to be equal. So we have the specific current Is being equal to I0 e to the kappa Vt0 over ut, and it's also equal to 2 mu Cox ut squared over kappa. So the whole model, including both the first term involving the source and the second term involving the drain, would be something like I is equal to SIS times log squared 1 plus e to the kappa Vg minus Vt0 minus Vs over 2 ut minus log squared 1 plus e to the kappa Vg minus Vt0 minus Vd over 2 ut. So this model is an interpolation model that goes smoothly from the exponential form, which is our weak inversion model, to our square law model, which is our strong inversion model, and does so continuously in between. And it turns out that this model does a very nice job. I'll show you some slides now. So this is a different slide deck than the one we were working through, which I made more recently, which I like a lot better. So here, ID is the current that we had called I before. It's the drain current. It is expressed in terms of the difference between a forward current component and a reverse current component. The forward current component has this expression involving the source, and the reverse current has the same expression, only it involves the drain voltage. So it's SIS times log squared 1 plus e to the kappa Vg minus Vt0 minus Vs or Vd, depending on whether you're talking about the forward current or the reverse current, over 2ut. So here S is the strength ratio, W over L. Is is 2 mu Cox ut squared over kappa. It's called the specific current. Ut is the thermal voltage, Kt over Q. And kappa is this capacitive voltage divider between the gate and the surface. So Cox over Cox plus C depletion. Here the specific current times the strength ratio turns out to be just about twice the saturation current that the device will have when it's just at threshold, when the argument of the exponential up here is equal to 0. So it turns out that log squared 1 plus 1 is a log squared of 2, and that turns out to be like 0.49 something something something. So it's very close to a half. And so it's approximately twice the saturation current just at threshold. So here is what the saturation current expression is again. In saturation, basically the forward current term is much larger than the reverse current term, and so the current is just equal to the forward current term, which is the saturation current. And in weak inversion, this form limits to the exponential model, and in strong inversion, it limits to this quadratic form. And here, this is a plot showing current through an Nmos transistor, and it's the same type of transistors that you guys would be using in the labs, the ALD 1106. And the red circles are measured values of channel current as a function of gate voltage. And here I've got the transistor diode connected, but I could also have it with VDD on the drain, and it would be just about the same. And here is the weak inversion region, and here is the exponential model. You can see that it does follow. The black line is the Ekv model, which is what this model is called. Ekv are the initials of the people who invented it, Enz, Krummenacher, and Vitto, a bunch of Swiss guys working at EPFL in Luzerne, Switzerland. And so you can see that in this region, the black line and this straight line here, which is the exponential subthreshold model or weak inversion model, are on top of each other, but they very rapidly start to deviate from each other as we get into this. This is the moderate inversion region here. And then in strong inversion, you start to get the current bending over like this, and this light gray line here, which approaches a vertical asymptote at Vg equals Vt0, is the quadratic model. And you can see that up here, the quadratic model and the Ekv model are exactly the same. But in this transition region, both the exponential and the square law model rapidly diverge from this Ekv model, which does a very nice job at capturing the behavior of the transistor, much up to, say, 3 or 3.5 volts of gate voltage. You start to get a little bit of that mobility reduction that I talked about high up in strong inversion kicking in and making the current bend over a little bit because mu is being reduced. But this model does a really nice job. So here, kappa from the best fit model turns out to be about 0.737, which is pretty much what we said it would be when we talked about weak inversion operation. And the threshold voltage that it found was about 0.577 volts. Threshold current, SIS, is about 1.5 microamps. Okay, and the actual current is about a factor of 2 less than that. If you look over here, this is a factor of 2 on the log scale, and it's about exactly that distance below SIS. here. It turns out that when Vg is equal to Vt0, the current predicted by the weak inversion model is just SIS. And so here at threshold, the extrapolated subthreshold or weak inversion model is SIS, and the difference between the actual current and the extrapolated weak inversion model is basically just a factor of 2. So that's that. If we look at the transconductance gain of the transistor, which is di sat dVg, this is what we would see. So this is basically numerically differentiating that gate characteristic, and this black line that kind of curves along here is the Ekv model for the transconductance gain, which works out to be this expression when we express it in terms of the saturation current. And in weak inversion, we have a translinear type relationship where the transconductance is just proportional to the current, which is pretty much like what we had with the BJT, only in this case it's the saturation current instead of the collector current, and we get a factor of kappa out front instead of just I sat over UT, it's kappa I sat over UT. In strong inversion, it turns out we get a different power law relationship for the transconductance gain. It turns out the GM is proportional to the square root of the saturation current. And so the transconductance gain predicted by this Ekv model does a very nice job at following the transconductance of the device all the way through the transition region, whereas both of these extrapolated weak inversion and strong inversion models don't do so good as we get into this transition region here. So these are drain characteristics plotted on a log scale, and you can see that in weak inversion and moderate inversion the saturation voltage is pretty well constant as a function of current level all the way down. It's about 4 UT, which is about 0.1 volts. And then as we get up into strong inversion, which would be around here, it starts to expand out. And so to the left of this dashed line here is the ohmic region, where we have Ohm's law-like behavior. And to the right of this region we have the saturation region, which is current source-like behavior. So I think that's all the characteristics I have to show here. You can see that this Ekv model does a very nice job, even though it has basically just the IS parameter, the kappa parameter, and the Vt0 parameter. It does a very nice job at capturing the gross characteristics of the device in terms of like the approach to the saturation region and the behavior of the device all the way through from weak inversion, moderate inversion, into strong inversion. It's continuous. It goes without having any if statements in it, and it admittedly is a little on the complicated side, but what that means is that if you know that your device is going to be operating in weak inversion, or you know it's going to be operating in strong inversion, you would want to use the simpler asymptotic forms that the Ekv model reduces to in weak inversion or in strong inversion. Okay, so that's it for this one.